Hello everyone. Simple linear regression. That section of analytics where you see an overlap between statistical learning and machine learning. If you use it to understand association between dependent and independent variable, it will be towards statistical side. And if you primarily focus on using regression model for prediction of unseen data, it will be more towards machine learning. A simple yet most powerful tool in the realm of analytics. Welcome to my YouTube channel. This is Ahmed Zaidi, working as Chief Data Scientist. And in this space, I create contents on a topic relevant to analytics and challenges a data scientist faces in their daily work. So let's go cracking. Simple linear regression is a statistical technique that is used for finding the association relationship between dependent and independent variable. As you can see from the equation, y is the dependent variable that depends on x, beta 0 and beta 1s are constant and slope, and epsilon is the random error. The same is depicted in this picture here, where on the x-axis you have independent variable x, and on y-axis you have dependent variable y, and this line, which is red in color, is the regression line. There are many use cases where simple linear regression is used in industry. Some of the applications are listed here. For example, if we want to understand the relationship between salary and number of years in terms of experience, or if we want to understand the relationship between waiting period and net promoter score in a call center, then simple linear regression is the tool to go. Okay, so let's have a look at the code. First, I'll import some standard libraries into my notebook. I'll be using matplotlib for visualization, pandas and numpy, stats model that I'll be using for model building, and sklearn for test train split and for calculating accuracy. So let's run this. Let's get the data. The data that I'm using here is life expectancy data from Kaggle. Now this is the data provided by World Health Organization. It gives details about life expectancies in different countries. If we look at the first 5 rows of data, we have the country in the first column, year in the second column, which is like year in which data was collected, starting from 2000 to 2015, status of the country, life expectancy in number of years, adult mortality, which is like how many adults per thousands death are there, infant death, death due to different factors, GDP of the country, population. Towards the end, we have one more variable, income composition of resources. Now, this is the factor which indicates that how well the productive resources are being used in the country. It ranges from 0 to 1, and higher the factor, the more productively the resources are being utilized. Schooling, that is in number of years. Let's look at the shape of the data. 2,938 rows, 22 columns. Let's look at some basic information about all the variables. We have these many non-null values, data type for this data. Let's look at some of the statistics. Now, if we see now life expectancy and income composition of resources are our variables of interest because we are looking at simple linear regression. We should have one independent variable and one dependent variable. Life expectancy is our dependent variable for this tutorial, and income composition is what I'll choose as independent variable. Now, if you see income composition, it varies from 0.94. It has a maximum value of 0.94 and different statistics. Let's look at the null values in our data. Now, our dependent variable life expectancy have 10 nulls, while our independent variable income composition of resources have 167 nulls. To keep things simple, in this tutorial, I'll only subset data for year 2015, and I'll take these two components out of data. And let's look at the shape. So we have 183 rows left now with 2 columns. Uh, Now we have to treat these null values. One of the ways to remove them completely, and there are other ways also available where you can just replace these values maybe with the mean value for 2015 or median value depending on what make more sense for you. Let's see now, since we have these many null values, what I'll do, I'll just remove these. I'll drop this, and then let's check how many still remain. So we got rid of 10 observations from the data. Okay, so having after having a look at these simple properties or statistics about the data, we will now move on to the exploratory data analysis part. I would first like to see the distribution of my dependent variable life expectancy, and I would like to see a plot, a histogram plot. Now, if you see here, we have most of the values concentrated at 75 years, a tail this side and a shorter tail this side. Data looks a bit skewed, but let's go ahead with this. Let's have a look at our independent variable income composition of resources. Now here also we see a peak at around 0.8. We see a small tail this side and a smaller tail towards right. Okay, then quickly check the correlation. Now there is a very high correlation of 0.91 approximately between our two variables, which is a good sign. Let's plot this in a heat map, 0.91, so all good. Let's see a scatter plot. It's a very good idea to plot a scatter plot when you are doing regression because that gives a visual relationship. Now, what I can say from here is that there is a linear relationship between two variables. If you see all the data is getting concentrated here. Let's go ahead. Model training. So in order to train the model, we have to separate out our dependent and independent variable into two different series, X and Y. I'll do this. Then I'll use train test split to make different series. I'll use 20% of my data and I'll keep it as out of sample data. I will use this data to test my model once it's done to see how my model reacts when it will be used against the data which it has never seen during the training exercise. Let's do it. Let's check the length of our training data, which is 138 rows. Good. I'll convert all these series to NumPy arrays because that's what my stats model accepts. I'll then add a constant and then I'll train a model and I'll fit it. So my model is done. I'll then print the summary and here it is. In this section, you will see some basic details like your dependent variable, ordinary least square model, and stuff like that. Now here is the main stuff, R square, which is 0.821, quite good. Now R square, this is coefficient of determination. It explains or it determines that how much variance in your dependent variable is being explained by independent variable. In other words, better the R square, better the model is in terms of fit. So we have 0.82, which is quite good. Now this is adjusted R square. So what happens with R square is as you add more independent variable, R square increases. Every time you add a independent variable, it will go high. Adjusted R square takes into account these additional independent variable and it will bring down its value. So if you are adding some crap, those independent variables which will not make sense to the model, it's better to use adjusted R square to determine how well your model is getting fit. All right. So we'll have a look at the probability, overall significance of the model, and this is very low, which is a very good sign again. This indicates that if the probability, overall probability of our model is less than 0.05, then our overall model is very significant. AIC and BIC. So AIC and BIC, they are pretty much used when you have multiple model at your hand and you need to select some or one. Lower the AIC, Akaike information criteria, or Bayesian's information criteria, better or parsimonious the model is. Let's move on to the another section. And here is what you have some statistics about your constant and your coefficient for the for your independent variable. Okay, so these are the same values which we saw in our equation for straight line y equals to beta 0 plus beta 1 x plus epsilon. Now this is the constant and this is your coefficient for your independent variable. What this means is that for every unit change in x, your y will change by 45.2986. The probability value for this is 0, which is pretty good, which indicates that your independent variable is quite significant for this whole regression exercise. Okay, so I'll come to this section a little later when we talk about diagnostics, and here we are. Okay, so regression diagnostics. Now, when we do a regression exercise, we assume certain things, and our model holds good only if those assumptions are true, or if those assumption holds, then our model holds. If not, then we are in the wrong direction and we need to take some steps in order to have stable predictions. Now to test those assumptions, there are some tests available, some statistical tests available. I'll talk about few in this tutorial, and maybe in next sessions I'll try to cover some of the remedies that you can take. So the first test is the normal distribution of residuals. Now the residuals, the error part of our equation has to be normally distributed. That is first assumption. And to test this, we have Jark-Barra test and omnibus test. Now, null hypothesis of these tests says that residuals are normally distributed. So let's see Jark-Barra test. I'll just run this. We have the p-value, which is quite low, very close to 0, skewness and kurtosis. Now, we see that our residuals are negatively skewed, and the kurtosis, and we have a kurtosis value which is positive. So this indicates that our residuals are negatively skewed and the 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 curve is little flat in nature. Let's see what omnibus test has to say. Again, the probability is quite low. Okay, so based on these two tests, we can say that our residuals are not normally distributed. All right, so what that means? This means that we have to do some remedial methods, and then only our predictions will be reliable. So let's move on to the next test, the test for heteroscedasticity. So one of the assumption again in regression is that residuals do not depend on your variable x. They should be independent. To test this, we have a test which is Bruchbagen test, And the null hypothesis in this is that there is homoscedasticity, which means that there is no heteroscedasticity. Let's do this test. So p-value is pretty low again, which means that we have to reject the null hypothesis and we have to say that there is heteroscedasticity. All right, so in the above two tests, we have seen the two problems. Now in this tutorial, I'm not going to go into the details how to remove these issues or how to deal with these problems, but I'll try to make another session, another tutorial on how we do this. But just to give you an essence, few of the methods that can be used uh, to deal with these issues is by transformation. So you can take log transformation, you can do square root transformation, you can do inverse transformation, you can take square, exponential, whatever fits your data. And here is where your skill will be tested. You have to come up with all these creative transformations so that you get rid of these issues in your models. Let's move ahead with the third test, the test of linearity for your model, Harvey-Collier test. And the null hypothesis here says that your model is linear. And let's see if our model is linear. Yes, it is. Because you have the p-value which is greater than 0.05, your null hypothesis holds. All right, so we are done with the test, but just a word of caution here. Before you move into the production with these kind of models, you have to deal with the issues that I have discussed earlier. And this is very, very important. Most of the data scientists fails here. Okay, so let's just to wrap up this tutorial, I will move ahead and use this model for prediction. Let me just do the predictions on my training data and see, um, and then because I'm very much interested in checking how it performs on out of sample data, I take my prediction and I print my predictions here. Let's see the R square. That's 0.83, which is quite good. So my R square is good. I also want to see what my mean absolute error is, which is 0.28. That's also nice. So with this, I have concluded my predictions and I'll share the GitHub link of this code with you guys. Bonus tips for you. So linearity condition in regression is defined with respect to the coefficient of x here. The equation that you see in green is right form of regression, although you see a square here, and that is because beta 1, the coefficient, is linear. Whereas the second one is not the correct form of regression because your coefficient of x is not linear. Another tip, you should only be using your regression model to predict those values of y which corresponds to the values of x that are there in your training dataset. Alright, so if you enjoyed this video, then please like and subscribe my channel. Thanks for watching and take care.